Okay, good afternoon class. Let's start the tutorial class today. So welcome back to school. I hope that you did have a good time during the Easter break. And I also hope that you didn't forget everything you learned before. But just in case you did, here is a little review for you. So to recall what was taught, what you have just learned right before the spring break, here are a summary of some formula that are commonly used for calculating the confidence intervals. And there are different scenarios. Under different scenarios, according to what information we have, we need to use different formula. Okay. So once you can identify for a particular problem what formula is suitable, then everything will become straightforward, just routine calculations. So the crucial part is under what scenario, you need to be very clear under what scenario we should use which formula. So first of all, we have the situation when you are given a sample. You have some sample statistic, you have some sample data, and you are also told that the sample was drawn from a normal distribution. Then we will use this formula. For the confidence interval of the population mean, there are also two different situations whether you have the information about the population variance. If the population variance, sigma square, is known when it is given, then we will use this formula to calculate the confidence interval. So you can see the sigma appear here because you know the value, so you can use this formula. And in this quantity, we have the sample mean, sample size, and population standard deviation sigma. Besides, we also need this quantity, which is a quantile from the standard normal distribution. So it is the notation representing this quantile. So this is the quantile. 1 minus alpha of 2, it depends on the coverage we need for the confidence interval. Then Z 1 minus alpha 2 is the quantile at which the area to the left-hand side under the standard normal curve is equal to 1 minus alpha 2. So that we have the coverage in between equal to 1 minus alpha. This is the standard normal curve. And this is obtained by using the standard normal distribution table or by using R. Now in case when the population variance is unknown, when it is not given, but you have the sample standard deviation, you have the sample variance, then we will replace sigma by S, which is the sample standard deviation. But after we change it into S, we also need to change the quantile. The quantile will be no longer the normal quantile. It will be the quantile from the student T distribution table. Okay? And in the student T distribution table, besides the quantity of this area, 1 minus alpha 2, we also need to provide a so-called degrees of freedom. This degrees of freedom takes the value of n minus 1, where n is the sample size. And it can be obtained by using the student T distribution table or by using R. I will show you how we can do it by using R. Now, besides the confidence interval for the population mean, we may also want to find the confidence interval for the population variance when it is unknown. And this is the formula. And in this formula, it is no longer taking this form with a quantity plus and minus another quantity. It will be obtained by these two numbers, the lower boundary and the upper boundary of this interval. Both have the same numerator. Now notice that in the lecture notes, probably you will see another form of this numerator, but they are equivalent. Probably in the notes, okay, you'll see that the numerator of this confidence interval is represented by this, which is the sum of the square deviation of each data from the sample mean. But it is actually equal to n-1 multiplied to the sample variance. Because if you divide by the sample size minus 1, it will give you the value of the sample variance. This is the formula for calculating the sample variance. So this and this are equivalent. I like to use this just because sometimes, most of the time, the information provided in the question will be the sample variance. So we can directly use this. And the denominator here, they are the quantile obtained from the chi-square distribution and also obtained using the chi-square distribution table or by using R. So this is the situation when we have a single sample drawn from the normal distribution. Now sometimes in the question, it is not told, you are not told that the sample is drawn from normal. You are not told that the population resembles a normal distribution. So we may have a sample from unknown distribution. Now, we can do it by using normal approximation in case when the sample size is large. If the sample size is large, then we can approximately calculate a confidence interval for the population mean using the same formula. You see, this formula and this formula are the same if the population variance is known. But if the population variance is unknown, we'll use this formula, but the quantile is no longer t. We'll still use the normal quantile. The reason is that if the sample size is large, if n is large, this degree of freedom is also large, then t will converge to normal. So we can just simply use the normal quantile. So this is the situation when the sample size is large. So you may wonder, what would we do if the sample size is not large? Then you may need to use some so-called non-parametric method that probably you will learn in higher level course. Now there are some other problems that you are asked to calculate a confidence interval for the population proportion. And this is the formula for calculating the population confidence interval of the population proportion. And we also rely on the situation when the sample is large enough. If the sample is not large, probably you may need to use some other method, more advanced statistical methods. So if we have a large sample from a Bernoulli distribution, Bernoulli means there are only 1 or 0. Okay? Each observation is only a classification, 1 or 0, success or failure, yes or no, something like that. Then the confidence interval for the population proportion is computed using this formula. Now notice that this S bar is actually the average of this 1 and 0. And essentially it is the sample proportion. Okay? So for the population proportion, we make use of the sample proportion plus minus a normal quantile and multiply to this quantity. In fact, this quantity is the standard error of this. For the mean and proportion, they usually will take this regular form. We have an estimate of the unknown quantity that we want to estimate, plus minus a quantile from a table, multiplied to a quantity which is just the standard error of this estimate. So for the mean problem and the proportions problem, we usually have the confidence interval with this regular form. So this is a summary of what you've just learned before the break about confidence interval. In fact, besides one sample problem, we may also want to do two sample comparisons. That means, suppose we have two independent samples drawn from two populations. They may have their own population mean, their own population variance. And we would like to compare the population means by calculating a confidence interval for the difference. Then there are different scenarios depending on whether we know the value of the population variance. If the population variance are known, we will use this formula. If where this M and N are the sample sizes of the two samples respectively. If the population variance are unknown, there will be also two different situations, whether we assume that they are equal or not. If we believe that the two population variance are equal, although we don't know the value, then we use this formula. And we have a common estimate of the population standard deviation if we assume that they are equal. We call this the pooled sample standard deviation. Pooling the two samples together, computing a quantity that estimates the common population standard deviation if we believe that they are the same. Then we use this formula, and the quanta will be also from a T distribution. But this time the degree of freedom is the combined degree of freedom of the two samples. The sum of the two sample sizes minus 2. This is why we used it for two sample comparisons. But there will be some situation that we don't know whether they are equal or not. We may not be able to assume that they are equal. So if you have you encounter this situation when the population variance are unknown but unequal, then we need to use this approximated formula. So notice that we have no common estimate of the population variance anymore. So we need to do it separately. And for the T quantile, the degree of freedom will be computed by using a very complicated formula, very hard to remember. Okay? We call this the Satellite approximation. I don't know whether you will be asked to do this calculation in your test or final assessment or not, but for completeness, because I see this one also appear in your lecture notes. Finally, we also have the comparison of population proportions. Suppose we have two large independent samples from two populations. Each of them has their own population proportion. We want to compare them by calculating a confidence interval for this. Then this will be the formula, where M and N are the sample sizes of these two samples. Okay? So these are the commonly used confidence interval formula that you learned so far. Okay? Any question? So the crucial point is that you need to identify for a particular problem which formula you should use, and then you use that to do the calculation. Now in this worksheet, example sheet number 9, basically you just need to use the formula for the one sample cases. Okay? And for the next worksheet, then you will need to use those for the two samples. Okay? So maybe you can start to spend a little time work on question number 6. So based on the information given in the question, just try to think about what formula we should use for confidence interval of mu and for the confidence interval for sigma squared. Just let me know if you encounter any problem. No, this is just a summary. You can have those formulas. Degrees of we don't have the summary. Those formulas are also. Okay. Maybe you can take a screen cap.
So 20. Yeah, 98%. So that half is. Yeah, so 2. Oh, yeah, because you need, so the n minus 1 is 29. Yeah. 1 minus after the 2, so that's, you need that side of the table, and that side of the table.
Is that which is there from?
Yeah, it's part of the same. Those are the two things. It's Approximation, so.
Oh, it would be that interval is between those two.
Okay.
Again. The confidence interval is anywhere between those two values.
So that is the interval.
Yeah.
Okay.
Yeah.
Okay, I can see some of you are on the right track that picked the correct formula. So to answer this kind of question, first of all, you will need to identify what scenario we are in. For example, we see this keyword, normally distributed. So we are told that the sample was drawn from the normal distribution. And we also see this keyword unknown. Okay? Sigma square, mu and sigma square are unknown. So the population variance is not given. So therefore, according to these formulas, we can see that when we have a single sample from the normal distribution with the population variance not given, then this will be the formula that we should use for calculating the confidence interval for the mean. And this will be the confidence interval for the population variance. So we'll need to use these two formulas for this question. So we start with the confidence interval of the population mean. And in this formula, we already have the population mean, the sample mean, which is given as 127.442. We have the sample standard deviation because we are given the sample variance. The sample size is equal to 30, also stated in the question. So what we need is just this quantile, the T quantile. And since we want the coverage of the confidence interval to be 98%, so that means the value of alpha is equal to 0.02. So 1 minus alpha over 2 is equal to 0.99. So the T quantile would be the quantile obtained from the T distribution with degree of freedom equal to 29, because sample size is equal to 30. The degree of freedom is sample size minus 1. So we want to find the 0.99 quantile. And it is equal to 2.642. That can be obtained from the student T distribution table. Or you can use R. We call that in the lab. You have already tried to do a lot of calculation using the function to compute the quantile of different distribution. So the function starts with Q if you want to find the quantile. And then the keyword corresponding to the distribution. For the T distribution, the keyword of course is T. So Qt is the function to obtain the quantile of T distribution. And you need to provide the value of P, which is 0.99, and the degrees of freedom, 29. Then you can easily obtain this table values, 2.462. Of course, you are also recommended to try to use the table so that you can get familiar with how we can use the table to obtain this number. But anyway, after we have all this quantity in the formula, we can substitute everything into the formula. The sample mean plus minus the quantile multiplied to the sample standard deviation, which is the square root of the sample variance, divided by the square root of the sample size. So the rest will be routine computation. So you can use your ordinary calculator to get all this result. Expressing into an interval, it will be from 1 to 0.46 64 to 134.24. So this is typically how we can construct a confidence interval for the mean if we have a sample from the normal distribution, and also when the sample when the population variance is unknown. Now for the confidence interval of the variance, we use the formula n-1 s squared over chi squared, n-1, 1 minus alpha over 2. And same numerator, also the chi squared quantile. So we have the sample size, we have the sample variance, and what we need will be just the quantile. And both of these can be obtained from the chi-square distribution table or by using R. Again, we find the quantile, we start with Q, followed by the keyword of the distribution. The input will be the value of P and the degree of freedom. And we also need the quantile, the 0.01 quantile. So this will be the two quantity we need to put in the denominator of the formula. So we substitute into the formula. So at the end, we obtain an interval for the population variance. Okay. So this is how we can construct a confidence interval for the population variance. And usually, this interval will be pretty wide for the variance. Is there any question? Now, let's consider another question in the problem sheet. Question number 5. Now, this question is not exactly asking you to find a confidence interval, but it is something related to the confidence interval. It says that we would like to find a sample size, the number of measurements we should take, in such a way that the confidence interval of the mean reaction time will have a width no greater than 0.02. So this is another direction of a problem. You are given a condition or a requirement that is in terms of the width of the confidence interval. We want the width of the confidence interval not too wide, not exceeding 0.02. And then we want to determine the sample size required to achieve this requirement. Okay. So try to work on this question. And here is a little hint. I can show you here, and then you can hit the screen. This is for the single sample. So probably I will find a way to see how I can share it to the platform. I'm still new to this system.
Or is that G squared? Nothing else. Well, yeah, that's 0.7 and 0.8. So let's say 0.79.
That's 0.975.
Oh,
0.975, so halfway between 0.07 and 0.08.
Wait, is this one?
Nah, 0.9 is
0.9 side and then
0.075.
I see. So, well, it's point 0.83.
The other courses are just different number.
Okay, I see some of you got it all right. So first of all, to answer this question, we need to first identify what confidence interval formula we should use. So according to the information given in the question, we are also told that the sample is drawn from normal distribution. And the population standard deviation, sigma, is also given. So the sigma is known. So this is the formula we can use. But we are not asked to find the confidence interval. We are just provide a requirement that we want the width of this interval to be no greater than 0.02. Now, this is the form of the interval. The width of this interval will be the distance from this number to this number. So that means the difference between them. So if you take the difference between these two numbers, it will be just simply twice of this quantity. So the width is equal to 2 times this. Okay, this is the width. And according to the question, we want this width to be no greater than 0.02. So that means we are actually given an inequality. And based on this inequality, we want to find the value of the sample size to achieve this inequality. So we solve this inequality step by step. And because we are also given that sigma is equal to 0.5, okay? 0.5 or 0.05. 0.05, okay. So we can replace sigma by 0.05. So the sample size needs to be greater than or equal to 5 times this normal quantile, and then this square. So it depends on the coverage of the confidence interval we need. For example, for a 95% coverage, the corresponding normal quantile is 1.96. So that the sample size need will be 5 times 1.96 and then square. Oh. Yeah, about 96.04. So need sample size at least 97, because sample size must be an integer. Okay, so this is how we answer this kind of question, and it is also a typical situation when before we draw the sample, we need to decide the sample size. How large a sample should we take? Well, we have some requirement. We put some precision requirement. We want the interval to be narrow enough so that it will be informative. So we want the interval to be no greater than 0.02 with the width. Then we can determine the sample size we need. And you can just try to find the sample size need if we want the coverage to be 99%. Okay. Now, because time is running out, so maybe I will just directly walk you through on another question. So this is a typical question on how we can calculate the confidence interval, not for mean, for proportion. So we are asked to find a 90% confidence interval for the proportion. So for the proportion, we are given this formula. Okay? For a single sample with large sample size, this one, the confidence interval for the population proportion is obtained by this formula, where what we need will be the sample size, the sample proportion, and also the normal quantile. Now, since we want a coverage of 90%, so alpha is 0.1, so the normal quantile will be the 0.95 quantile. From the table or from R, you can find that it is equal to 1.645. So we substitute everything into the formula, and we also need the sample proportion. We are not exactly given this quantity, but we are told that out of these 500 households, 80 of them were found to have 3 or more TV sets. So the sample proportion will be obtained as 80 divided by 500. So this is how we obtain the sample proportion. So the confidence interval would be equal to 0.16 plus minus this normal quantile multiplied to this standard error. And the sample size, 500. Okay, so this is how we construct a confidence interval for the population proportion. Is there any question? So all these are just some typical scenario and common scenario. We calculate the confidence interval based on a single sample. And in the next worksheet, you will have some more exercise on how we can do two sample comparisons. Okay? Just feel free to let me know if you have any questions. So see you next week.